Hi. Now we will start a lecture in a series of lectures which we will talk about the PCB design to make it EMC compliant, so that we will use the knowledge of how the electromagnetic noise is coupled to the surroundings, and that knowledge will be then applied to design PCBs in a way that they will be as good as possible in terms of radiation and also in terms of immunity. And the first lecture in this series will be talking about the EMI generation mechanisms. Let's start now. So EMI generating mechanisms. How the electromagnetic noise, EMI, is also states for electromagnetic interference. How this noise, how this electromagnetic interference is generated in PCBs and how we can then minimize it. And this is our main task as PCB designers. So let's go. This is just to give you a boost, let's say, about how we should care about EMC at the beginning of the stage of developing a new product. So here at the beginning we have a lot of solutions available, and we can do it already very well just by choosing the correct design strategy. And later on, when we go into the testing, then we have less and less options to repair it. When we find out that something is going wrong, that we have emission too large, too extensive, and we want to minimize it by adding extra components, extra filters, and these are possibly the most expensive solutions, adding extra additional filters to cables, using better cables, using everything to minimize the problems that we already did in the beginning of the design. And later on, when the product is going into market, we have almost none solutions left. If it is found out that it's not compliant, we have to redraw it and remake it, reinvent the thing that we already did, and that would cost a lot of money. So thinking at the beginning about EMC would make your life as an engineering easier. And here I show you two designs of students. The same problem was solved in this EMC competition that we have each year, and here you see a good design and this is a bad design. And please note that both of these students were excellent students, passing this exam as well with the highest grade. But there was a little bit of a difference between these two solutions. One of these students just forgot a little bit of maybe 1 or 2 millimeter long line that was placed incorrectly, and the result was devastating. So it is quite often a problems of details. Therefore, I cannot stress enough actually how this is important. And that's why we will go into details during this lecture. Okay, and the topic of this lecture would be sources, noise sources in the EMC field of electronics, the noise sources in PCBs. Because minimizing noise sources at the beginning is a thing to do, because then you don't have a problem if your noise sources are minimized. Then you don't have a problem of reducing the coupling paths and shielding and filtering and stuff if your noise source at the beginning is already minimized. And the truth that was told by this guy who wrote a book about EMC is that if you want to comply with all the rules that you have, every rule that you may think of, you want to do it perfectly, then you will end up with the worst design, much worse than it might be by not knowing these rules. Because the thing is, you cannot apply rule to every single aspect of the PCB. Every single small piece of PCB cannot be done perfectly, because then you would have to sacrifice other parts. So idea is to identify the most critical parts of the PCB and do them as best as possible, and then do the rest. You cannot apply the same rule to every piece of the PCB at the same extent. Okay, this picture shows the basic sources of electromagnetic noise on PCBs. When we are talking about electromagnetic noise, then we have to always consider the type of the PCB that would be the cause of that. And of course, usually what we have to have in such a PCB in order to be potentially dangerous for EMC is high current and voltage, fast current and voltage changes. So we need I will do it in this way, pen, okay. So what we need du over dt, and we need the I over dt. So we need high current and voltage changes in time, because these then couple by a capacitor or inductive coupling. This is inductive coupling, this is capacitive coupling, and these two couple to the rest of the world, let's say. And therefore, such high voltage and current changes are usually found in digital circuits, when you have digital ICs, the digital microcontrollers, FPGAs, digital logics, memories, and communication lines. And that's an example of such a PCB, quite simple, I would say, in principle. So that PCB has a microcontroller, yeah, it has some sort of a driver interface, and it has a connector. It has a power supply, and at the beginning of the power supply we have a voltage regulator. So what kind of noise sources do we have here? The main noise source, of course, is the fastest digital logic you might have. Like, for example, this microcontroller here. And that one is the noise source by itself already. So it has some internal circuitry that switches very fast. So we have fast current and voltage changes. And that microcontroller itself, it's already a noise source. But then this microcontroller is connected to some interface, some digital stuff here. Let's say this is an Ethernet interface. So it has some fast connections to this Ethernet interface. So there are fast voltage changes on these lines as well. So the noise also comes, and I would say mainly then comes from these lines. So these lines are radiating away electromagnetic noise. Then this driver interface itself is then connecting to the connector. So again, these lines on the connector coming to the connector are also radiating. But not just that. If there are several lines, like here for example, and here as well, they also have so-called crosstalk. A crosstalk would mean that a noise from that line is coupling to the other one, that one and that one to that one, and maybe in between each other. So we have crosstalk, we have radiating noise from the fast digital lines away, and every line on the circuit, I would say, to be brief, to sum it up, will be a potential noise source. Every digital line that contains high voltage changes and current changes in time, it will be a potential noise source. What about DC current and DC voltage? A DC current and DC voltage will not radiate by itself. So then we are safe on the power lines, right? Here. But actually not. Why? Power line may contain DC voltage, of course, but the current that is taken by this fast digital integrated circuit is certainly not DC, because they are fast switching devices. So the current taken is an fast changing digital waveform of different size of spikes that are then summing up together to a certain level of current. So that current certainly not DC. And this current is then taken away from the voltage regulator here and it spreads over these long power supply lines. So these long power supply lines are also source of radiation, even though you have DC voltage on them. And that current noise then actually is transferred either also through the regulator voltage stabilizing circuit here and can spread away along the cable. And that cable then can radiate. So this we have conductive noise coupling and also radiation noise coupling. And on the other side we have communication cable that also contains fast switching voltages and currents, and it can radiate by itself because it has to contain these signals in order to communicate. On the other side, the power supply input should be ideally DC. Therefore, this radiation here is unwanted and we have to filter it here. So we have to put some filters if we cannot do it otherwise. Okay, these are then the noise sources mostly. What about, let me summarize maybe just to make it clear. Summarizing noise sources would mean that every current and voltage change requires like that. So current and voltage change du over dt and di over dt is a potential noise source. And it could be a voltage on a certain line, so like that, or it could be current running in a loop, like that. So that's the current that flows in a loop. Okay, I'll do it again. Maybe I'll do it indifferently. So that's the voltage on the line, du over dt, and that's the current in a loop. And the radiation is electric field here, and here we have magnetic field. Yeah? So these are noise sources. It could be any digital switching pin or current, high-speed current running through lines. What about the susceptibility to noise? So the immunity part. Okay, some parts of the circuit are also very sensitive to noise coming from inside the circuit or from outside. For example, in this picture here, a digital clock line is shown here. That clock line or some other line that contains high-speed signals can radiate as well. But it can also be susceptible to outside input noise that coming from outside the circuit, because it is a very sensitive, depends on the type of the line, of course, and the way it's routed, but it contains signal which is very, very important. If you have this clock line that is sensitive to noise and it changes one single bit, then all the data will be corrupted. The other example of such lines are reset lines and other control lines that are controlling the basic operation of the microcontrollers or digital interfaces. And these are very sensitive to outside noise, and you have to be careful when you route them and when you shield them from the external noise. So I will show you in a few next slides which are of such lines that are sensitive to outside noise. But you should keep in mind that noise sources and sensitivity to the external noise comes hand in hand. If you make PCB that radiates very low, then you would also have a PCB that it's not susceptible to outside noise, that is, has high immunity. That's true for most cases. In some cases, it's not. Maybe later also about that, but right now I don't think it's relevant. So what can we do? Most of the EMC problems can be solved on the level of the integrated circuits. So, for example, here, if you can keep the fastest signals inside the chips, that's already quite a lot, because then you don't have to route them on the PCB. For example, microcontrollers contain external oscillators. They need them to operate. And some of the microcontrollers, or many now, require only 32 kilohertz quartz. 32 kilohertz. And then they multiply it inside by using phase lock loops, which are special circuits that are multiplying frequencies up to hundreds of megahertz if needed. So such a 32 kilohertz source would be then adequate for the microcontroller to internally run at 100 megahertz. So keeping all the fast signals inside and only the slow signals outside. The other option is very important, is optimal pin arrangement. Optimal pin arrangement means that you arrange pins in a way that they are easier to route, and therefore you can use the optimal routing technique. And some of the manufacturers know that very well and are doing their best to do so. Well, I will show you later on examples how this is maintained. So on the chip level, you can do really a lot. So the chip manufacturers, the chip designers are the ones who should really pay attention to the EMC later, because sometimes you could make such an IC in such a strange way that it will not be able to make it compatible. On the PCB level, we do all sorts of stuff. And I will not go here in detail because you will actually hear all that several times later. If the PCB is not adequate, then you have to go into the cable level to shield and terminate the cabling, ground correctly and filter the cables. Then on the module level, shielding the whole modules and grounding them. And finally, the software part is not negligible, especially fault masking and correcting, and watchdogs. These are parts of the software which are checking if everything is going okay, and if something goes wrong, it immediately resets the processor and starts it all over again. And that's an essential part of the software which helps with the EMC compliance. Just an example, if you have a device like a phone, for example, or anything more or less, and you use it in a more advanced level, let's say that the device is used to control some more high reliability equipment, and then that you have a problem of ESD, electrostatic discharge, when your body carries some charge and you discharge it into the device. That device, if it resets at that point, it has to be getting back into operation in a certain time. If it doesn't, then it will fail the EMC. So using correct software techniques to really quickly restart the device before you even notice, in some cases, it's an essential part of the EMC solutions. In the PCB design, we have several tracks which go in parallel, like here on this slide. So you should place the components, you should route them, you should route the power supply separately, and you should take care about the case and PCB stack up. So going from bottom up now, the case and the PCB, you have to define how many layers you will use, what will be the distances between layers, and you should choose the correct materials. And you should know about these materials in order to be able to choose the most suitable one and most cheap one as well. You should already have an idea how many layers you will need for such a design. Depends what you have. If you have control impedances, for example, of the transmission lines which you will use on your PCB, you have to have at least 4 layers, at least 4 layers, if not 6 or 8. If you don't use the controlled impedances, then you might get away with 2 layers. Depends on the density of the PCB. Then, on the other 3 parts, you have to identify critical components. You have to identify which components are those who are the most critical in terms of the EMC. The components which contain the highest du and di over dt. You have to identify all these components in terms of placement, routing, and power supply connection. And then you should do the connections of these components first. So this, let's say in the placement here idea, you have to do correct placement of these components together. So you are either group them together or you separate these components, depends on what you want. Because some of the components have to be grouped together to make the smallest current and voltage loops of the connections, and the others should be kept away because they are very sensitive and you do not want for noise to couple between these 2 parts of the circuit. And then you place the components when you do the grouping of different types of the components on the PCB. In the routing procedure, you do first connect critical signals and then the rest. Don't do everything optimally, as I said before. Do the ones which really require optimal connections first and do the rest as they please. On the power supply, you have to separate the groundings of different parts of the circuit, maybe connect the grounds together in the proper way. You have to separate the power supplies going to a very sensitive part and the part that contains a lot of noise. And then you separate them by bypassing and filtering using capacitors and coils. In the case and PCB level, you have to do the correct grounding of the PCB to the case and maybe some shielding if necessary. Shielding because you cannot achieve a proper enough low radiation just by putting components in the most optimal way, connecting them in the most optimal way, and so on. Maybe that isn't adequate and you have to do the shielding as well. So what are the critical parts? Of course, everything that runs fast switching devices like microprocessor, memories, communication chips. Switching power supplies, very important. All the power drivers for motors or solenoids or any high power that use switching as well, not just DC. High power means high current and high voltage. And if that changes in time because of the switching part of that drivers, that contains a lot of noise. Just imagine a motor, electric car motor driver, how much current that switches in very short time. All the signals that are running between these devices, all the clock signals, fast data buses, and also, as I told before, power supply lines, even though they contain DC voltage, they contain high current spikes because of the switching devices they are powering. And then on the other side, we have very sensitive parts of the PCB as well we have to care about, like all the digital inputs, like reset lines, interrupt lines, control lines, all the digital inputs that are highly sensitive because they are usually high impedance lines. And if you have a high impedance line, then you have a problem of coupling, because the coupling between the source and capacitive, let's say coupling scheme, if you have a high impedance line, this coupling between the mutual capacitor is large. So usually these digital inputs are high impedance inputs, therefore you have to lower their impedance and make them more firmly stable and resistant to external noise. On the other side, you have, so here I will just write digital, yeah, I will just write digital inputs. On the analog inputs and also outputs, we have different inputs for sensors, high gain amplifiers, voltage references, A to D inputs. Everything that is analog and it contains some noise, it's a problem, because the analog voltage is carrying information, and changing that information by adding noise, it's not acceptable. It deteriorates the system. So all the inputs that have high gains, all inputs from sensors and stuff, everything that is analog has a problem with immunity. Okay, so now we will do a little bit of a theory, because I was just telling you that here everything that is fast is a potential noise source. But how fast are we talking about? Is it like very fast, or what is fast? How does it look like? Okay, that's an example of a digital signal transition from 0 to 1, logical 0 to 1. So we have a logical 0 region, we have a logical 1 region, and the voltage changes between this and that region. And it has to change quickly if we want to transfer a lot of information in time. So that means that more the communication speed, the shorter the rise time. So that switch between logic levels should be fast. Therefore, rise time, or slew rate if you want. Slew rate is just the derivative of this signal here. Can be calculated by using this equation here. So that the rise time is a time between the 10 and 90% of the amplitude of the signal. So this changing in time contains high frequencies. Therefore, as I said, the problems are du over dt's, and the same for current, di over dt. And choosing this then and applying to a spectrum analysis, we get this. If we take an ideal trapezoid signal with rise time, full time, on time, and the whole period, and we calculate its spectrum, we get something like that. We have a base frequency here, 1 over t. Then we got the first corner frequency, where the high frequency component starts to decrease. This first corner frequency is defined by the on time. And then the higher frequency harmonics are decreasing by 20 decibels per decade, hitting the next corner here where the rise time is defining it. And from that on, you are continuing with 40 dBs per decade. Speaking in different terms, I would say that here this part is proportional to 1 over frequency, and this part is proportional to 1 over the frequency squared. And this is the corner frequency defined by the rise time, and this is defined by the on time. So which part of this frequency range of the signal is the one which is mostly dangerous for the EMC? And the answer is the high frequency part, of course, because at high frequencies the lengths of the connections are becoming also effective antennas, and therefore we have to care about the high frequency part. Now, which part of that signal changes the high frequency portion of the spectrum? And checking out here, it's not that obvious, because if you change, let's say, the T on time, you increase it, then this part, then this part would be going further. Yeah, so you would actually change that stuff, that part here. If you change the rise time, you would actually move this part away and or back, depends on what you do that change with, how you increase it or decrease it. So from the first glance, it's not that obvious, but let me do an experiment. So here I have a spectrum of a square pulse. I did it in SPICE, and it has 100 nano of period. So actually that pulse gives a base frequency of 10 megahertz. This is the fundamental frequency of 10 megahertz. Why it doesn't work all the time? So the fundamental frequency F0 is 10 megahertz. The T on time is 10 nanoseconds. So the first corner frequency, when it starts to drop for FC1, and here we have FC2, where it starts dropping by 20 dBs per decade, is around 30 megahertz. And at 1 nanosecond rise time, the second corner frequency would be in the range of 300 megahertz. That's approximate value, of course. So that's it, more or less. That's what we also observe from the frequency of such a signal. Here we have 20 dB per decade, and here we have 40 minus, of course. So now what we do, what happens if we change the base frequency? I decrease the base frequency by a factor of 10. So I went from 100 nanosecond to 1000 nanoseconds. So the base frequency is now 1 megahertz. The first corner frequency is now 3 megahertz, because I kept the duty cycle the same. I just decreased the frequency. And the rise time is defining the same second corner frequency, which is 300 megahertz. So I just decreased the frequency, but I did not decrease the rise time. So the pulses are really very sharp without a change. Now, what happens with the spectrum? It moves to the right. So all the spectrum is moving to the right. So I'm decreasing the portion of the signal here in the mid-frequency range, and I'm also decreasing the portion of the signal at the high frequency range. So here you see that's what happens when you change the frequency. Now what I will do now, I will go back to the main signal here, and I will decrease the rise times. So the rise times now are decreased and are now 100 picoseconds, 0.1 nanosecond. So the second corner frequency, the first two stay the same, the second one is then moved to 3 gigahertz, which is a lot, which is really a lot. So you see how the high frequency portion then increases. So both of the parameters are important. So if I go back, the period, the frequency, the base frequency, and also the rise time. But the part which defines the high frequency part of the spectrum and does not changes the rest is the rise time. So here, if I could then go to lower frequencies, it's important that I decrease the rise time as well. Because here I went to lower frequencies, and if I decrease the rise time with the same maneuver I did with the lowering frequencies, because lowering frequencies would mean lower speed of communication and also lower noise. But if you do not change the rise time with the lowering of frequency, you don't achieve much. Let's say if I increase now the rise time to a higher frequency, to a higher value, like for example, I would go with the rise time to 10 nanoseconds here. So I would do maybe such a case. Sorry, now this is not very good. But if I went like that, I could do that. Keep having much slower signals for the same amount of transferred communication information. I could then just lower the whole stuff again. So again, instead of for 10 nanoseconds, instead of 300 megahertz, I would have 30 megahertz of corner frequency, of the second corner frequency. I will do it a little bit better. Yeah, FC2 would be then 30 megahertz. And the consequence would be this. That would be additional improvement, which would be a really, really big improvement. So keeping the rise times at the minimum level is a must if you want to keep your spectrum of the signal at lowest value. So in digital signals like that, the rise time is the most important parameter to keep the EMI of your signal at low levels. Now, why are we caring about high frequencies? I already told a little bit about it, but here I state it again. The rule of thumb says if the length of the track is longer than the 1/20th of the wavelength here, then your line becomes an effective antenna. Control P. So lambda over 20 is an effective antenna. And high frequency part, therefore, is the most important one. And there, if you check the rise time, you will see that 10 nanoseconds would be, you would have antenna which is, let's say, starting to be critical at 50 centimeters. If you go below to 1 nanosecond, the 5 centimeter antenna would be already effective. Therefore, it's important to keep the rise times low, long as possible. And that's about it for the first part. And after a short break, we will move to the second part of the lecture, when we will talk about differential and common mode signals.